So residual plots are another use that we have for residuals. So not only is finding the line with the smallest square, a sum of squared residuals is our best line of fit, but we can also use residuals to decide if what we're looking at is actually something that needs to be, has a linear line fit to it. The residuals kind of give us a better idea of the shape of data. So a residual plot is a plot in which the residuals are plotted against the values of the explanatory x. So we're going to compare x to residuals. When two variables have a linear relationship, the residual plot will not exhibit any noticeable patterns. So what we mean is we expect to see something that kind of just is all over the place. There is no actual pattern to it. If the residual plot does exhibit a pattern, such as a curved pattern, then the variables do not have a linear relationship and the least squares line should be used. So sometimes you'll have something you think is going to be normal and you do its residual plot and it will do something like this. So you see like a definite pattern to the residuals that you wouldn't originally see there. So residuals kind of catch patterns and make them more obvious for us. So do not rely on correlation coefficients to determine whether two variables have a linear relationship. So we mentioned that before. We can have data that looks like it's pretty normal. And I might go through and go, hey, that looks pretty normal. We're going to do a linear relationship. But it may actually be that the data has a little bit of a nonlinear pattern to it. So like this data might actually fit a curve line. So sometimes it's a little hard to tell that. So we can't assume because the linear regression was good that it was actually a linear relationship. This is going to say it has a good linear relationship when in fact it's not even a linear relationship. So to determine whether two variables actually have a linear relationship, we are going to construct a scatter plot or what we call a residual. So the least squares regression line for predicting selling prices for from housing size is right here. We found it a couple times. It's y hat equals 160.1939 plus 0.0992x. The residuals and the residue plot, the residuals right here, sorry, and the residual plot are shown. So these are my residuals. So all I did was I plotted my x against the residuals. And what we see here is this data doesn't seem to have any pattern. And when we don't see any kind of definite pattern going on, then we can say that a least square regression line is appropriate for this data. No pattern. So this is the residuals, right? So we have no pattern in the residual plot. That means the data appears linear. And it is appropriate to model with a linear line. Or in our case, a least squares regression line. So if we don't see any pattern in the residuals, we can assume that that data actually probably has a linear relationship. Now, just for example, again, so the plot shown is the number of bottles of water that was consumed, and that is predicted by the length of a hike. So it's the distance in miles this person hiked, or people. So we see the data, it seems like it fits a linear model, but we're just going to double check that. So we make the residual plot, and what we see is there doesn't appear to be a pattern. There seems to be an even amount of numbers above and below the x-axis because we're going to have positive and negative residuals, kind of like we had here. So we see 0. So we got about the same number of points above and below. So that's another hint to look for. There's no obvious pattern. So this is evidence that a linear regression model is suitable to represent the relationship between x, and that should have been y. The y disappeared. That y kept trying to disappear the whole time I was making this. So here, these points, you could probably see that they do seem to have a curve pattern to them, but you could have looked at them and said, yeah, it looks like a linear line. So this is minutes given to a bacteria population and then measuring the size. So it's a population of bacteria. If we do the residuals, this curve that we saw here becomes very, very obvious in the residual. So if we weren't sure if data did have a pattern to it, the residual makes it more obvious that it is there. So this plot shows that most residuals lie below the x-axis, and there is a noticeable curve to the pattern in the scatter plot. So this indicates that this is probably not a linear model, and we should not be modeling it with a linear equation. Curve model would be appropriate in this case. And we're not doing a curve models. So for us, we'd go, well, there's nothing we can do. Okay, so example 1, for each of the following residual plots, determine whether a linear model is appropriate. As we see here, the blue line's marking your x-axis, or not your, well, yeah, essentially. So you're 0. We got about an even number of points below and above, and there doesn't appear to be a pattern at all. So this one here, we'd probably say, yes, linear model is appropriate. We see that points are evenly above and below the x-axis. And there's no pattern. So if we look at this other one, well, there's definitely a pattern there. So we have a curvy pattern. Because we see a definite pattern here, then we would say, no, linear model is not appropriate. Okay. So we want to make a residual plot for one of the following linear equations, and we want to determine if it is appropriate to use a linear regression model. So this was actually the line of best fit. So we're going to use this one. So it's probably not the best example, but we're going to assume that is my best line of fit and just find a residual plot. Well, we already know what the residuals are going to look like, but we just need to make the plot. Okay, so if we want to make my residual plot, actually, let's just clear all this out for right now. I'm going to put my x values in. So we had a 3, 5, 5, 6, and 7. So those residuals that we calculated earlier were 0, -1, 2, -0.5. Oops, I hit something wrong there. Let me go back and do that. 0, and then -1, there's my mistake, 2, -0.5, and 0. So we go to stat plot, second stat plot, turn on the stat plot, L1, so that should be my X. My Y list is going to be my residuals. I'm already on a scatter plot. So go to zoom, trace, and this is it. So it appears it's a little funky to look at, but I'd say, in my opinion, it doesn't seem to be much of a pattern here going on. You kind of want to go, it's like, yeah, that's a pattern, but we got this going on here. I think this is probably no pattern. Data can be modeled with a linear equation. Or least squares regression line. Or in other words, I can use the linear model for it. All right, and then just one more thing to kind of briefly talk about again. So we had talked about influential points. I think I called them influential outliers, but an influential point is a point that, when included in a scatter plot, strongly affects the position of the least squares regression line. So we're going to consider a scatter plot of farmland versus total area of the United States, which we had looked at before. So what we had seen before, and here's like Texas. So most of our data is here, and it's got a good linear relationship to it. And the blue line represents, like I said, least squares line for 48 states. So this is just in blue. This is the line if we exclude Texas and Alaska. So Texas has an abnormal amount of farmland, well, size and farmland, so it doesn't quite fit with the rest of the data. Alaska has a normal amount of size, but not as much farmland. So we have Texas and Alaska are excluded. So what we're seeing here is that if Texas was added, Texas is an outlier. Texas is definitely not close to the rest of the data. So if I include just Texas, what we see here is that my line does not vary a whole lot. It moves a little bit, but it's still pretty close to the same as the blue line. We exclude Texas and Alaska. Now, if we look down here, where we have Alaska, so if I just include Alaska, not necessarily Texas, but just Alaska, then we see the line gets pulled way away from the blue line. So the solid, like I said, the dotted line is the least squares regression line for the 49 states, including Texas. The inclusion of Texas moves the line somewhat. So what happens is it moves it somewhat. That means that Texas is not influential, or at least as far as this data goes. It's not an influential point. And it's not an influential point because it doesn't actually have a big impact on the data. So this was like with the sweets, when I removed the eating 23 sweets a week, it didn't have a big impact on my correlation coefficient or anything because it didn't really move the data that much. But with Alaska, we saw when we took out Alaska, everything moved significantly. So what we have here is that Texas is moved, and it's not an influential point because Texas is not influential. It's inclusion or removal. has little effect on the regression line. However, what we're going to see is that Alaska is influential. Alaska, when we put it in the data set, all of a sudden it just pulls that data way out of place. So the dash plot line of the least squares regression line, the 49 states, including Alaska, we see has a big shift in the position of the line. So Alaska is an influential point. Once again, it's inclusion or removal. So whether it's there or not has a big impact on the regression line. So we had measured this before, but we had measured it with a correlation coefficient. This time we're just doing it by looking at the regression line. So if my regression line only moves a little bit, the point wasn't very influential. If my regression line moves significantly, then it is an influential point. So influential points can be troublesome because the least squares regression line is supposed to summarize all the data rather than reflect the position of a single point. When a scatter plot contains outliers, the least squares regression line should be computed with both with and without an outlier to determine which outlier is influential. If an outlier is influential, the best practice is to compute the least squares regression line with and without the point, and the equation of both lines should be reported. So we have to look for those influential points because we have to look at what happens to the data when it's there and when it's not there. So just because we have one outlier doesn't mean that maybe there actually is other outliers elsewhere in the data. If we had, more of the data. So we can't completely just ignore it because it may be very important to how the data looks, but also we want to have a good predictive model of what's going on. So sometimes we need to remove that point so our model's a better predictor.